In December 2025, researchers reanalyzed data from NASA's Cassini mission and discovered something scientists weren't expecting. For nearly 2 decades, planetary scientists maintained that Saturn's largest moon, Titan, concealed a global ocean of liquid water 50 to 100 kilometers beneath its frozen crust. Radio tracking data from Cassini's 124 flybys indicated the moon flexed under Saturn's gravity in ways that suggested a massive subsurface sea. But the new analysis, published in Nature, showed a different picture. Titan's interior dissipates 3 to 4 terawatts of energy as heat through tidal friction. That's enough power to run 1/4 of human civilization. The researchers noted this level of energy dissipation is not consistent with the presence of a global liquid ocean. Instead, Titan's interior appears to be composed of thick ice layers, transitioning into slushy zones, with isolated pockets of water near the rocky core. This discovery forces scientists to rethink one of the most intriguing worlds in our solar system. Titan has fascinated astronomers since Dutch scientist Christian Huygens discovered it in 1655. At 5,150 kilometers in diameter, it's larger than the planet Mercury, and the second largest moon in the solar system after Jupiter's Ganymede. But distance makes it difficult to study. Titan orbits Saturn at 1.2 billion kilometers from the Sun, 9 times farther than Earth. Sunlight there is just 1% as strong as what we receive. NASA's Voyager 1 probe flew within 4,000 kilometers of Titan in 1980, revealing a thick nitrogen atmosphere completely obscuring the surface with orange haze. Instruments detected nitrogen, methane, ethane, and propane. Surface pressure measured 1.5 times Earth's, with temperatures hovering around -179 degrees Celsius. Cold enough that methane, which exists as gas on Earth, behaves like water does here. Voyager detected hydrocarbons everywhere, but the surface remained a total mystery behind impenetrable atmospheric haze. Scientists knew they needed better tools to reveal what lay beneath. The Cassini-Huygens mission launched in 1997 as a joint effort between NASA, the European Space Agency, and the Italian Space Agency. After a 7-year journey, Cassini entered Saturn orbit in 2004, carrying the Huygens probe, specifically designed to land on Titan. Huygens separated from Cassini on Christmas Day 2004. 3 weeks later, on January 14, 2005, it began its historic descent through Titan's atmosphere. For 2.5 hours, the probe parachuted through the haze, transmitting temperature, pressure, wind speed, and atmospheric composition data continuously. As Huygens dropped lower, the haze thinned and the surface came into focus. Cameras captured rolling hills, dark channels carved by liquid flow, and scattered rounded pebbles. When Huygens touched down, it became the farthest human-made object to successfully land on another world. The landing site resembled a dried riverbed on Earth. Those pebbles were chunks of water ice, frozen harder than granite in the extreme cold and coated in sticky organic material. Huygens even detected a brief release of methane vapor from the ground on impact, indicating the surface was slightly damp with liquid hydrocarbons. But Huygens sampled only one location. Cassini, orbiting Saturn, conducted 127 close flybys of Titan over 13 years. Using radar to pierce the atmospheric haze, it mapped nearly the entire surface. Cassini's primary instrument for studying Titan was its radar system, which transmitted microwave signals through the thick atmosphere and measured the reflections from the surface below. Unlike visible light, these radio waves penetrated the orange haze completely. The spacecraft also carried the radio science subsystem, As Cassini flew past Titan, ground stations on Earth precisely measured tiny changes in the spacecraft's velocity, caused by variations in Titan's gravitational field. These shifts corresponded to changes in the Moon's shape as Saturn's gravity squeezed and stretched it during its elliptical orbit. This tidal flexing creates friction inside Titan, generating heat that dissipates into space. By measuring how much Titan deformed and the timing of that deformation relative to Saturn's gravitational pull, scientists could infer the Moon's internal structure. The limitation: interpreting this data requires complex modeling. The same observational data can support different internal structures depending on the assumptions built into the models. That's where the 2025 reanalysis becomes significant. Cassini's radar revealed stable bodies of liquid on Titan's surface, concentrated mostly in the North Polar region. The largest, Kraken Mare, covers 400,000 square kilometers, bigger than Earth's Caspian Sea. Ligeia Mare and Punga Mare follow. These seas contain liquid methane, ethane, and dissolved nitrogen, with depths reaching 300 meters in some areas. The surfaces are remarkably calm. Waves rarely exceed a few millimeters in height. Titan's dense atmosphere and low gravity dampen wave formation, despite conditions that should theoretically produce larger waves. The radar also detected what scientists call magic islands, bright patches that appear on the seas, linger for hours to several weeks, then vanish. A 2024 study analyzing Cassini data proposed these are chunks of porous, honeycomb-like organic solids, frozen hydrocarbon snow that breaks off from eroding shorelines and floats on the denser liquid ethane, similar to icebergs on Earth but made of organic ices. The porosity allows methane to seep in slowly enough that the clumps linger at the surface before eventually sinking. Away from the poles, vast dune fields stretch thousands of kilometers across the equator, with dunes hundreds of meters high. These are composed of tholins, complex organic compounds formed when ultraviolet light and cosmic rays break apart methane molecules high in the atmosphere. The fragments chain together into heavier particles that fall as reddish snow. Cassini also identified potential cryovolcanoes. Features like Sotra Patera show a deep pit, flow-like structures, and a mountainous rim, suggesting eruptions of slushy mixtures of water, ammonia, and methane instead of molten rock. The gravity and rotation measurements showed Titan deforms by more than 10 meters in elevation as it orbits Saturn. This was twice the value predicted before Cassini arrived. For years, scientists interpreted Titan's extreme tidal deformation as evidence of a subsurface ocean. A deep, liquid layer would allow the icy crust to flex more easily under Saturn's gravitational pull than a completely frozen interior. Cassini's gravity measurements indicated Titan's interior was more deformable than expected for a solid body. The prevailing model suggested a water-ammonia ocean 50 to 100 kilometers deep, sitting beneath an ice shell and above a rocky core. This ocean could theoretically mix surface organics downward through impact craters, creating environments where Earth-like prebiotic chemistry might occur in liquid water, similar to the subsurface ocean of Saturn's moon Enceladus. However, the energy balance presented challenges. Flavio Petrica at NASA's Jet Propulsion Laboratory noted that if Titan had a global ocean, the moon shouldn't emit as much heat as observed. Most frictional heat from tidal flexing would go into keeping the ocean warm and liquid, rather than radiating into space. Additionally, this energy dissipation should have circularized Titan's orbit over time, but the moon still follows an elliptical path. The December 2025 reanalysis detected a 15-hour delay between when Saturn's gravitational pull is strongest and when Titan shows maximum deformation. This delay indicates substantial energy dissipation in the interior, approximately 3 to 4 terawatts, corresponding to a tidal quality factor Q of approximately 5. The research team, led by Patricia with contributions from Baptiste Journeau at the University of Washington and colleagues at multiple institutions, found this signature of tidal dissipation is not consistent with a global subsurface ocean. A liquid layer reduces the tidal dissipation generated below it. The new analysis does not prove Titan lacks any subsurface liquid. The models indicate the interior structure is more likely composed of high-pressure ice layers, including Ice 3, Ice 5, and Ice 6, close to their melting points. These layers can contain slushy zones with small amounts of partial melting. Localized pockets of liquid water could exist near the rocky core where temperatures are higher. These isolated reservoirs might host chemical reactions between water and rock, but they would not form a planet-wide connected ocean. The study also does not rule out the possibility that future modeling with different parameters could accommodate a global ocean. Luciano Yes at Sapienza University of Rome, who was involved in the original Cassini research, noted that removing Titan from the family of ocean worlds requires very strong evidence. What this discovery does show is that a single dataset can support multiple interpretations, depending on modeling assumptions. The debate continues as scientists refine their understanding of Titan's interior structure. Importantly, this finding does not address Titan's surface chemistry or the complex organic molecules in its atmosphere. Those observations remain unchanged. Titan forces us to reconsider what defines a habitable environment. On Earth, liquid water is essential for life as we know it. Titan's surface temperature of -179 degrees Celsius makes water-based biochemistry impossible at the surface. But Titan's atmosphere is a natural laboratory for prebiotic chemistry. The haze produces molecules including hydrogen cyanide, benzene, and long carbon chains. Cassini detected heavy, negative ions in the upper atmosphere, indicating massive molecules too complex to identify directly, possibly precursors to amino acids or nucleotide bases. Recent observations from the James Webb Space Telescope in 2023 and 2024 added crucial details. Webb detected the methyl radical, CH3, for the first time in Titan's atmosphere. This highly reactive molecule with an unpaired electron forms when sunlight or energy from Saturn's magnetosphere breaks apart methane molecules. Stephanie Milam at NASA's Goddard Space Flight Center described it as seeing the chemical cake while it's rising in the oven, instead of just the starting ingredients and final product. Understanding this intermediate step helps scientists model how methane converts to ethane and other hydrocarbons. Webb and ground-based Keck telescopes also observed cloud convection in Titan's northern hemisphere for the first time in July 2023, showing active weather patterns replenishing the methane seas. On Titan's surface, tholins accumulate in quantities surpassing Earth's oil reserves by hundreds of times. Scientists detected vinyl cyanide, or acrylonitrile, in the atmosphere. Laboratory experiments show this molecule can form stable, cell-like membranes in liquid methane called azotosomes, a hypothetical alternative to phospholipid cell walls. Whether Titan could host exotic methane-based life remains speculative. Without a global ocean mixing surface organics with subsurface water, the chemistry stays more isolated. But isolated water pockets near the core, combined with surface organic chemistry from meteor impacts that temporarily melt ice, could still create environments where prebiotic reactions occur. The December 2025 Nature paper prompted immediate responses from space agencies worldwide. NASA's Jet Propulsion Laboratory emphasized the discovery underscores the value of archival planetary science data, noting that sophisticated analysis techniques can yield new discoveries years or decades after missions end. The European Space Agency indicated that combining ground-based observations with Webb telescope data and archival Cassini information provides crucial insights into Titan's atmosphere. ESA noted these findings will inform possible future missions to the Saturn system, currently under consideration. The discovery has implications for how agencies interpret data from other icy moons. Jupiter's Europa and Ganymede, along with Saturn's Enceladus, have been identified as ocean worlds based on similar tidal deformation measurements. Multiple space agencies may need to re-examine those interpretations using updated modeling techniques developed from this Titan analysis. For NASA's astrobiology strategy, the finding shifts investigative priorities. If Titan lacks a global ocean, future exploration will concentrate on surface chemistry, impact crater sites where water ice melts temporarily, and potential isolated subsurface water pockets rather than searching for a planet-wide habitable ocean environment. The reanalysis demonstrates how missions continue delivering scientific value long after they end. Cassini concluded its mission in 2017, yet nearly 8 years later, improved analysis methods are still producing fundamental discoveries that reshape planetary science models. NASA's upcoming Dragonfly mission, scheduled for 2028 launch, will provide direct measurements to test these competing interior structure models when it reaches Titan in 2034. Titan represents a unique natural laboratory for understanding how organic chemistry evolves in the absence of life. The Moon's thick atmosphere and surface conditions may resemble early Earth before biological processes began, offering insights into the chemical steps that preceded the origin of life on our planet. The question of Titan's internal structure matters because it determines what kinds of chemical environments exist. A global ocean would provide a warm, liquid environment where water-based prebiotic chemistry could occur alongside the surface hydrocarbon chemistry. Isolated water pockets offer more limited but still potentially significant reaction sites. Understanding these environments guides how scientists search for biosignatures or chemical complexity that might indicate life or its precursors. The distinction between a planet-wide ocean and slushy layers with isolated pockets changes the mission design for future landers and the specific locations they should target. The broader implication extends to exoplanet science. As astronomers discover worlds orbiting other stars, Titan serves as a nearby example of how complex chemistry can arise without biology. It shows that detecting organic molecules in an exoplanet's atmosphere does not automatically indicate life. Titan also demonstrates that habitability requires specific conditions beyond just the presence of liquid and organic molecules. Temperature, energy sources, and the ability for different chemical reservoirs to interact all play roles. NASA's Dragonfly mission remains on schedule for launch in July 2028 aboard a SpaceX Falcon Heavy rocket. The nuclear-powered rotorcraft will arrive at Titan in 2034 after a 6-year journey. Dragonfly will use 8 rotors to fly hundreds of kilometers across Titan's surface, hopping between dozens of sites. The thick atmosphere and low gravity make Titan an ideal environment for aerial exploration. The mission will sample dunes, impact craters including Selk crater where organics mix with water ice, and regions where liquids once flowed. Its instruments will directly analyze organic compounds and search for chemical signatures of both water-based and exotic methane-based processes. Dragonfly will also carry seismology equipment to probe Titan's interior structure, potentially resolving the ocean debate definitively. Whether Titan harbors a global ocean, slushy layers, or isolated water pockets, this moon continues to challenge our understanding of planetary science and the conditions necessary for life. Does Titan represent a laboratory showing prebiotic chemistry without biology, or could it host some form of exotic life we haven't imagined yet? The next decade will bring answers that reshape how we think about habitability in our solar system and beyond. What do you think Titan's interior holds? Let me know in the comments. If you enjoyed this deep dive into one of the solar system's most mysterious worlds, hit that like button and subscribe for more space exploration discoveries. All visuals in this video are illustrative and created for educational purposes, based on proposed engineering concepts discussed in scientific research and official space agency publications.